in large structures, use cold dark matter. Okay, but if you try to use cold dark matter, which is non-interactive in small structures, for example, structures in the order of 1 megaparsec, which is like groups of galaxies clusters, or galaxies itself. These kinds of structures can't be fully described by only non-interaction cold dark matter. Okay, it needs to be, when you compute this in a simulation, it doesn't correspond to our observations. So one of the ways you can resolve this problem is to use models for self-interacting dark matter. Okay, so for example, in a galaxy, in a spiral galaxy like this, you have a bulk, a dark matter halo, in a cold dark matter halo to form, but the velocity of the structures, for example, let's not get a galaxy, let's get a group of galaxies. It's better. The velocity in the center or in the inner space of this bulk of dark matter, cold dark matter, it's greater than it should be. So one way of alleviating this is to implement a mediator for this dark matter, and this mediator are gonna create, for example, the interactions for the dark matter, the scattering, and this scattering is gonna decrease this temperature, decrease this velocity of the dark matter, and we can fit the observational data. Okay, so that's the basic idea of self-interactive dark matter. Normally, for galaxies, groups of galaxies, this interaction particle, which is, for example, a dark photon, which is in this article A prime. This A prime needs to have a mass around in the order of MeV, the MeV scale. For example, 10 MeV. Okay, so there needs to be a way to create this kind of mediators in the universe, and for this paper, it uses a U1 prime symmetry break. Okay, but I'm going to talk about this later. So having these kinds of mediator, you can kind of solve this small scale structure problem. Okay, this is one part. The other part is related to gravitational waves. So as I said, recently there was shown signals of high frequency nanohertz gravitational waves, so low frequency gravitational waves. And this kinds of signal, it could be generated, for example, for a first order phase transition. Is one of the ways that this signal, this nanohertz signal of gravitational waves could be generated. First order phase transition. And for the nanohertz gravitational waves, this first order phase transition should be around the MeV scale as well. So the idea of this article is, okay, we have this signal. This signal could be generated by a first order phase transition, which happens in the MeV scale, in temperatures of MeV, so right before the BBN. And this kind of mechanism could generate this dark photon, which is needed in the small scale structure problem to solve to fit the observational data using computational simulation. Okay, so there's a link between the two ideas. Okay, the Lagrangian for this is in the second part. No. Cima? Okay. Not that. Okay, so the Lagrangian of this U1 prime is this. Okay, so you have the term, the Dirac term for the dark matter, so self-interact dark matter, and this D is related to the dark form, which is Z prime, and it comments the interactions between the dark photon and the dark matter. Okay. You have okay. So to generate this first order phase transition, you need to have a potential, okay, which changes with the temperature, which is this potential here. And the plot of this potential is in the end of the article. Here is the potential. Just this plot. Okay, so this is the potential. This curve here, it gets lower as the temperatures gets lower as well. So here we have the curves of the field for the temperature of the critical temperature, which is the temperature that you have two minimum points for the field. And when the temperature evolves, it gets lower. You have one critical point here, one minimum point for the field. And this minimum point generates the mass that you can use to be the mass of the dark photon for your model. Okay? So we just okay. So I don't know, what's this? The article used these 4 benchmark points, which are benchmarks for the mass of the dark matter, the mass of the dark photon, and those benchmarks they computed more, but those benchmarks are good for this article because they fit both the needed masses for the small scale problem and the needed masses for the first order phase transition, which generated the gravitational wave signal. Okay, so these 4 here in this picture. Last one. This is the velocity of the systems. For example, groups of galaxies, flushes of galaxies. This is the mean velocity. This is the thermal cross-section, which depends on the velocity of the dark matter, the mean velocity of the dark matter particles. And as you can see, these points here are the group of galaxies, the clusters of galaxies, and this region here is a region which favors the dark matter self-interacting model. And as you can see, those 4 benchmarks that they use pass through exactly these points, which is common. There are other articles show these kinds of results as well. But the thing is, these same results can be used as well in this plot with the gravitational wave density, which is just the part of the density related to the gravitational waves in the universe. And there, in this frequencies. So these here are the CPTA data and the nanograph data, and those same branch marks that they used pass through both these measurements. So they can be used, they are in the same range because they are in map, the mass of the interaction, the mass of the dark photon is in maps, the first order phase transition occur in maps, and they use both of two to fit points which are related to the both of the scenarios, the gravitational waves with the first order phase transition, and the small scale problem with the cold dark matter. Okay, so it's basically it's the link between the two.
Awesome. Any questions? No?
If I got it right, then we have this dark book. And the dark matter candidate is a scalar.
No,
It's a
in
frame.
this case is I think it's a vector because it is from the Dirac equation.
Okay,
So
it's a frame.
it's a frame.
But, okay, so
The Lagrangian. And then in the next
I was just trying to understand how they.
It is. So there are two
It's
vectors. So
scalar.
there's the n chi and n phi.
But is the scalar that will break the symmetry and produce.
Oh, previous studies show that a dark matter candidate with m chi and GV and a mediator with mass ma, then you can fit well the data from dwarf galaxies. In our model, the ESCOLA, mediator ma around 10 to 15 is gas generation. On the other hand, CDS indicates
So basically, he's saying that there is a gauge boson which has a mass around NV scale, and then the breaking of the symmetry happens exactly because this guy will acquire mass. So in this.
yeah, so phi is the mass of the mediator that breaks whatever.
The dark matter mass is in
Yeah.
Jeff. It's in Jeff.
It is. Chi is the Dirac dark matter candidate.
You say GV, NV,
GEV. Okay.
EV, GV, NV.
MEV.
Okay, nice.
What?